We have so far learned that all matter is made up of little tiny balls called atoms, and we've learned that they are indivisible. Democritus said that there were an infinite number of kinds of atoms. It turns out that that's not true. We only have a limited number of kinds of atoms, and we'd like to take a closer look at that in this video. We will also peek into the atom, and here we see that the atom is indeed divisible. We can separate the atom into its constituent parts, and we'll look at what those parts are. But first, let's talk about the kinds of atoms. Well, it turns out that we only know of about 100 different kinds of atoms, and you can think of these as the bricks or the building blocks of everything that we see around us. The scientists give them a name. We call these the elements, and we've put them into a neat little table called the periodic table that shows us all the elements that we know of, and I'd like to show you that now. So this is the periodic table, and it might look a little intimidating at first with all these numbers and symbols on here, but the big picture that I want to get here is that these symbols here represent the building blocks, so they're like Lego bricks, if you like, and by putting together these Lego bricks we can make new things, or you can think of them as letters of the alphabet. So by putting together letters of the alphabet we get words. So the letters of the alphabet are like these elements here, and when we put them together we get the stuff that we see around us. So we'll come back to the periodic table in a moment, but next let's take a peek into the atom itself. So what we'd like to look at now is the actual structure of the atom, what it's actually made up of. So call this the atomic structure. Now, if you were to look inside an atom, I suppose you would probably be quite disappointed, because what you would see most of is just empty space. So most of an atom is empty space. But if you look really closely, right at the center of the atom, you have what we call the nucleus. So if this were an atom, then right in the center we have the nucleus. And in the nucleus there are two different types of particles. One we call the protons, which I'll draw a couple of here. So I have 4 protons, and some other particles called neutrons. Draw these in green. And surrounding the nucleus, in a simplified view, you can imagine that surrounding the nucleus we have these particles called electrons, kind of like orbiting the nucleus like planets orbit the sun. Now I should emphasize that this picture of the atom is not entirely accurate, but for our purposes currently it should suffice. So these things are called electrons, and they're moving around in what we might like to call shells. So we have these 3 things that the atoms are made up of: the electrons, the protons, and the neutrons. Now it happens that the protons have a positive charge, while the electrons have a negative charge. In a ordinary atom, you would have the same number of protons as electrons, so that the net charge is 0 overall. So for example, if you had 4 protons, you would have 4 electrons. And finally, these things that we call neutrons actually don't have any charge. But for now, what I want to draw your attention to is the protons, because this is what defines an element, or what defines a kind of atom. It is the number of protons that tells you what element an atom is. Well, so if we were to look at the periodic table and take a look at the key, it tells us that the top number here tells you the number of protons there are in a particular element. So for example, let's look at hydrogen. Hydrogen has 1 proton. So anything with 1 proton, any atom that contains 1 proton in it is hydrogen. We could have called it, element with proton equals 1, or maybe P1 in short form, or we could have called helium P2 and lithium P3, etc. So, but we happen to have given them names. So aluminum is an atom that has 13 protons in it. So any atom with 13 protons in it is aluminum. Likewise, any atom with 28 protons in it is nickel. We just happen to call it nickel. We could have called it atom with 28 protons. Anything with 26 protons in it is iron, etc. And for any one of these atoms, the number of electrons would equal the number of protons. So for example, copper would have 29 protons and 29 electrons, so that the charges cancel each other and it is overall neutral. Now I'd like to define a couple of terms associated with the atom so that it could help us in our analysis later on. So first, let's look at how we might represent an atom or an element. Say I have an element, I'll just call it X. X could represent any of the elements we saw in the periodic table. And just to be redundant, since the element, the number of protons actually defines what element is, I could, just write this element and we know what it is. But to give it a bit more information, sometimes what you might see is, you might see a number on the bottom left corner of the symbol for the element. This number is what we call the atomic number. And what the atomic number tells us is, it tells us the number of protons associated with this element. And as I mentioned, this is redundant because the name of the element should give away its number of protons, but sometimes it's hard to remember how many protons an element has, so we put that number down there. And a universal symbol for this number is Z, so don't have to worry about that too much. And just to give it an extra information, we might like, for example, to find out how many neutrons there are in an atom. Now, the number of neutrons doesn't actually affect the properties of the atom. It doesn't change what element it is. I could have any number of neutrons in an atom and it still stays the same element. Remember, the element is characterized by the number of protons it has, not the number of neutrons. So it turns out that the number of neutrons doesn't really matter all that much, but we'd like to put that information in. We could have just written the number of neutrons on the top left corner, for example, but for historical reasons we've chosen to write instead the sum of number of protons and neutrons. So if you see a number on the top left corner of the atom, what that number represents is the number of protons added to the number of neutrons, such that if you want to find out the number of neutrons, you would need to take the top number and subtract the bottom number. Now, this number, usually you give a symbol A. I don't know why you call it A. It's a bit confusing because the atomic number starts with an A, so you would think that we would write A for the atomic number, but it turns out that that's not the case. So let's take a look at several examples to get comfortable with this notation that we could use later on. So I might look at, let's see here. So I'm gonna take carbon, for example. So carbon, you might have a carbon with a mass number of 12. I beg your pardon, this number on top is also called the mass number, and we'll see in a later video why it's called the mass number. Is actually a meaning to that. So anyway, back to this carbon atom. The bottom number is 6. This tells me that this carbon atom has 6 protons, and the top number is 12. Now remember, the top number is protons plus neutrons, so if I subtract the bottom number from the top number, I get 6. So I get 6 neutrons for this guy, and if it's neutral, I will also have 6 electrons. Let's take a look at another example. Take a look at sodium, which happens to have symbol Na, which derives from its Latin name natrium. That's why it's Na. So for example, I have sodium. Sodium is element number 11, so it has 11 protons, and say this guy has a mass number of 23. Let me just write sodium here so you know what it's called. So this number is 11, and so bottom left number, atomic number of protons. So this guy has 11 protons. So any atom that has 11 protons in it, we call it sodium. And if I wanted to find out the number of neutrons, since the top number is protons and neutrons, I would subtract the bottom number from the top number. If I subtract 11 from 23, I get 12, and hence this atom has 12 neutrons. And in order for it to be neutral, since the protons are positive, I also want the same number of electrons to neutralize it. And let's do one more, just for good measure. Let's look at iron. Iron is symbol Fe, because the Latin name for it is ferrum. And iron is element number 26, and say this particular flavor of iron has mass number 56. So the bottom number protons, so 26 protons. To find the number of neutrons, I take the top number, subtract bottom number, so 56 minus 26. That's 30 neutrons. And for balancing the protons, I'm going to put 26 electrons. Now it turns out that this number of electrons can change. We'll talk a bit more about electrons because that's important in determining the chemical properties of a particular element. But in this case, I'm assuming a neutral atom, so I'm having it have the same number of electrons and protons. Now, I mentioned earlier that number of neutrons doesn't really affect the properties of the atom, the chemical properties, that is. It does affect its mass, however. And it turns out that in nature, you do sometimes get atoms of the same element that have a different mass. And the thing that affects the mass of this atom would be the number of neutrons. For example, there's another flavor of carbon that you see. If you were to dig a piece of carbon out of the ground, for example, as a piece of diamond's made up of carbon, you would find that some percentage of it is made up of this carbon with 6 neutrons, and some percentage of it is made up of another flavor of carbon, which happens to have 8 neutrons in it. Hence, it has a mass of 14. So this is carbon, So it has 6 protons, and 14 minus 6 gives me 8 neutrons, and since it's neutral, I'll put 6 electrons here. So in order to identify or to differentiate between these two flavors of carbon, we call them different names. For this, with a mass number of 14, we call this carbon 14 to indicate that it's got a mass number of 14. And for the carbon with mass number of 12, we call it carbon 12 to indicate that it is a carbon with a mass number of 12. Now, there's a name we give for these kind of sister atoms, if you like, and these guys are called isotopes of each other. This is a big word to mean that they're sisters or brothers. They're the same element, but they happen to have different masses. So as another example, let's take a look at sodium. Sodium happens to have 2 siblings. There is sodium 24. Since it's still sodium, still 11 protons. And then we have sodium 22. So this particular flavor of sodium has 13 neutrons. It still has 11 protons since it's sodium. And this particular flavor of sodium has 11 neutrons. Now this doesn't really change its chemical properties. It does change its mass, but they do sometimes have some special properties that we won't go into too much, but it's called radioactivity, and basically sometimes certain flavors of the atom, like carbon 14 here, is radioactive. Its nucleus will spontaneously emit particles, while carbon 12 is the more stable species of carbon and doesn't its nucleus doesn't spontaneously emit stuff. So to summarize, I like to make a table of some of the properties of these so-called subatomic particles, the electrons, the protons, and the neutrons. So we have, I'm going to write P for proton. Let's just write it out: protons, neutrons, and electrons. First, let's take a look at the masses. So mass in kilograms. Mass of the proton happens to be 1.673 times 10 to the minus 27 kilograms. So it's tiny. It's a tiny mass, and it almost takes up no space at all. So and the neutron is only slightly heavier at 1.675 times 10 to the minus 27 kilograms. So it's a decimal point followed by 26 zeros and then 1675 kilograms. So it's a tiny mass. An electron, compared to the protons and neutrons, is almost massless. You can see here that it's almost 10,000 times lighter than, or 100,000 times lighter than the protons or the neutrons themselves. So compared to protons and neutrons, they are the electrons are almost negligible in mass. And another property we could look at is their charge. So the charge on a proton is in arbitrary units we would call it +1, but it's actually 1.67 times 10 to the minus 19 coulombs, coulombs being the unit for charge. And the electrons would have a corresponding minus charge. You'd have the same charge, minus 19 coulombs, whereas the neutrons have no charge at all. Now, to simplify matters, we sometimes like to give the protons a mass of 1, and the neutrons, since they're almost the same mass, it's It's almost 1 2. It's not exactly 1. It's 1 point something in, you know, in units that we'll look at in a while. They're not arbitrary. They're defined based on a certain standard, but for our purposes we'll just call the protons as having mass 1, neutrons having mass 1, and since electrons are so tiny compared to the protons and neutrons, we just give them a mass of 0. And then the charge on the proton would be +1, charge on neutrons 0, and charge on electrons, I beg your pardon, charge on electrons -1. So we will be using these later on, which is why I'm introducing them here. So in this video we've looked at, we've peered inside the atom, and we realized that we've come quite a ways from where Democritus told us about his atomic theory, and we've learned about how to denote a certain species of atom using mass numbers, symbols, and proton numbers. So in the next video, I'd like to take a closer look at the electrons, because it turns out that electrons have an important role to play in chemical reactions.